Put these on.
Hey! Stay away from me!
I'm telling you, you dumb son of a... I'm trying to save you and your family's life.
You couldn't even save your own!
I'm giving you a choice. Either put on these glasses or start eating that trash can.
Not this year.
Okay. All right. Okay.
Come on. Come on!
I don't want to fight you.
Come on!
I don't want to fight you. Stop it.
No!
Put on the glasses. Now hold on. You ain't the first son of a bitch to wake up out of their dream.
Want to get in shape? Join our mall walking program. It's free to join and comes with valuable discounts for select stores. To find out more information, visit one of our representatives in Central Court. We'll be happy to assist you. Thanks for shopping with us.
You've seen the sunset, right? And if you get up early enough, maybe you've seen it rise too. But have you ever wondered, if the sun rises every day and sets every night, where does it go when we can't see it? Well, nowhere. It's actually us that goes somewhere, because we're on the Earth, and our planet is always turning or spinning on its axis. Imagine a line passing through the center of the Earth that goes both through the North Pole and the South Pole. We call that invisible line the axis. Earth spins around on this axis like a top. This spinning movement is called the Earth's rotation, and the Earth's rotation is what gives us day and night, every day, all year. If you're on the side of the Earth that's facing away from the sun, as the Earth is spinning, it's night. If you're on the side facing the sun, it's, you guessed it, day. Now, hold on tight, because the Earth is actually moving in more ways than one. At the same time that the Earth spins on its axis, it also orbits or revolves around the sun. This movement is called its revolution. One full orbit all the way around the sun is one revolution, and the Earth takes 365 days, or 1 year, to complete a revolution. So have you got all of this so far? The Earth is rotating on its axis, creating day and night, and at the same time, it's revolving all the way around the sun. Now here's the thing. As the Earth is both rotating and revolving, it's not sitting straight up and down. Its axis is actually tilted, just a little. It's not all that much, but this tilt causes one part of the Earth to lean towards the sun, while another part of it is leaning away. This means that different parts of our planet's surface gets different amounts of sunlight and heat. So, why am I telling you all of this? Well, as the Earth travels around the sun, it creates a pattern throughout the year. This pattern happens over and over again, and I'm sure you've noticed it. At certain times of the year, you see the northern hemisphere leans towards the sun, and the southern hemisphere leans away. And at other times, the southern hemisphere leans towards the sun, and the northern hemisphere leans away. That pattern, my friend, is what makes seasons. When the part of the world that you're living in is leaning towards the sun, it's warm and the days are long. Summer. When you're on the part that's leaning away from the sun, it's cold and the days are short. Winter. In between, it's spring or autumn. If the Earth weren't tilted, we would have the same season all year long. So, revolution, rotation, orbit. Is your head spinning?
Is your head spinning?
Has there ever been an experiment done to prove that the Earth is revolving around the sun?
Yes, there was several experiments in the 1800s. Dominique Arago, Armand Fuseau, Augustin Fresnel, but one of the most famous was the Michelson-Morley experiment in 1887.
Let's assume the ether frame moves relative to the Earth from left to right. Michelson-Morley used a half-silvered mirror to split a beam of light so that it travels in two different directions along two paths of equal length. This is the light beam before it is split. Moving in a perpendicular direction to the ether frame, this beam would be blown off course and would have to travel a little further. Traveling back down this path again, perpendicular to the ether, would also move this beam off course, if the ether existed. This beam, moving parallel to the ether and in the same direction, would increase its speed. This beam, again parallel to the ether, but moving in the opposite direction, would be slowed down. Here the two light beams are recombined together, and if they are in phase, they will constructively interfere. But if the speed was different in the two paths, they would combine to give an interference pattern.
No. Tell us about that.
Well, they used light beams to measure whether the Earth was moving, and they found that there was no movement. The Earth has to be moving 30 kilometers per second to complete its annual revolution, and they found out that it wasn't moving in a very precise. Michelson could have calculated it to 1/100th of what he got in his experiment. That's how sensitive his instruments were.
What did the experiment involve in terms of apparatus, so we can get a concrete understanding of
well,
what they
if
found?
the Earth is moving around the sun, and we shoot that light beam in the direction that the Earth is moving, okay, and then we shoot another light beam perpendicular to that, well, the one that's in the direction of the Earth's movement should be impeded in some way if it's moving through space, whereas this one that's going perpendicular would not be impeded.
Why not?
because it's not going through space. It's just going north and south.
Okay.
Okay? And what they found, they expected to have a 30-kilometer difference between these two light beams. There was no difference. So the natural interpretation, and even Einstein admits this, Mach admits this, Born admits this, the natural interpretation is that the Earth isn't moving. So how do we get out of that? Well, you invent special relativity. And now you say, well, the reason that light beam wasn't affected when it went toward the motion of the Earth was because the apparatus shortened.
Huh?
Yeah, Michelson's apparatus shortened as it was going with the Earth in its orbit around the Sun.
Wait, you're telling me that the contraction of mass
Yes.
was invented to explain away the results of the Michelson-Morley experiment?
Yes, and that's what my book will tell you, and it's been admitted by all the scientists.
Well, isn't there any experimental confirmation that as you approach the speed of light, there's a contraction effect? The impression is that there's all kinds of experimental confirmation.
That was invented. There's no proof to it.
Really?
Yes, all the physicists will tell you there's no proof
Not
to
that
it.
I'm surprised, you understand.
Yeah.
I know what the scientific community is capable of in terms of mass deception. Evolution is a mass deception. But I wasn't aware that they don't really have any even purported scientific confirmation in terms of physical measurement.
No, nobody
of the contraction
measured,
effect.
Nobody measured a contraction. But they put it into a mathematical formula called the Lorentz transform, and it's probably the most famous equation used in physics today.
Does anyone expressly admit that, hey, we had to come up with this contraction effect because otherwise we're stuck with a motionless
Yes,
Earth?
the very guy who invented it.
Tell me what he
Lorentz.
admitted.
Heinrich Lorentz says, I don't have any other explanation to this experiment of Michelson-Morley unless I contract the apparatus. Otherwise, we're going to have to believe the Earth is standing still in space.
Unbelievable.
Yeah.
Can you give an approximate page reference for me for your book? I want to go back and read that right away.
I'll send you an email. I'll show you where it is.
Especially at the beginning of the picture and at the end, or the right side of the picture, that's where they say you'll see curvature. So we look and we have, I put a little gap between the line and the horizon. And there we go, looks perfect. Okay, and we're going to maintain that gap all the way across. You know, I can't believe they try to get away with this. You know, they say you can't see curvature, but then they see the building's lower portions disappearing and they yell curvature. But here we are. Here's the horizon, nice long patch of horizon, and let's look at the end. Perfect. Not an ounce of curvature. Okay, a word about zooming in with a telescope. There are people that think that I've spoken to that if you use a telescope, your horizon will be further. The stronger the telescope, the further the horizon will move away from you. Well, that's not the case. The horizon is determined and formed by the ground visually angling up to your eye level. As you see in the beginning of the video here, where he's zooming in across the water, you can see a horizon form, and then as he keeps zooming in, the horizon doesn't get further away, the horizon gets closer, and it gets bigger. He's zooming in on the horizon. That horizon is formed whether you're looking at it with a naked eye or a telescope. All of the telescope allows you to do is to see it larger. See this picture on the top here? If the lines were parallel and perspective wasn't a reality, then yeah, the stronger the telescope, you could just see parallel to the ground. But the fact is, perspective causes the ground to visually angle up. And where that intersects is your horizon, and it's regardless of whether or not you're using a telescope. They angle to the eye level of the observer. This image is a product of our eyes. These are horizontal parallel lines, yet we see them not as parallel, but on an angle towards a point in the distance. Now, of course, we know that they are parallel, but they visually are not. Here you can see parallel lines made up of bricks on the walls. The wall on the left, though, is headed out towards the horizon, and all the lines angle toward the eye level of the observer. The bottom ones angle up and the top ones angle down. This is a great illustration of how all the lines angle to your eye position. You can't deny it. All of the lines converge at a center point on the horizon called the vanishing point. Parallel lines above it angle down, the lines below angle up, the sides angle in. The vanishing point is the intersection of the horizontal and vertical axis of our eye position. It's parallel all the way out, parallel with the ground. That's why I say you can't look down at the horizon, because the horizon angles up to your eye level. The two, your eye level and the ground plane, are parallel all the way to the horizon. But it's the bottom ground plane that angles up to your eye level. Okay, here's a new slide. Here's a guy sitting in the middle of the ocean. You can see the water angles up and on each side of him to our eye level. It actually angles all the way around him. Just like looking down that long hallway, the floor angles up to your eye position, the ceiling angles down, the walls angle in. That's perspective. Here's another one with the guy in the boat. Whether he's in the hallway or out on the ocean, the ground plane angles up to your eye position. And so you can't see any ground past that point once it intersects with your eye height. So items or objects will be blocked, especially the ground, and then lower portions of objects beyond the horizon will have their bottoms blocked from view. And here's another one. You can see the water ramp up to the eye level, and the building beyond the horizon has its lower portions obscured. It's kind of like putting your thumb out at arm's length and putting it level with your eyes. You can block things much bigger than your thumb. That's due to perspective. And the same happens here. The further away that building is, the more of it gets blocked, starting from the bottom up. Okay, that concludes the first part, dealing with the that there's no curvature on the x-axis or the horizontal axis. Now I want to talk about the thin horizon, the fact that the horizon has no depth, and how that is completely consistent with perspective on a flat plane, and not consistent with a sloping ball and the horizon being a product of that curvature. It goes really fast. He doesn't stay there very long. I make a still of that too. I blow it up and you can check it out. Here's another zoom. Okay, check out the choppiness and the shallowness of the horizon. Okay, person who recorded that zoomed in so quick. I wish he would have stayed on the horizon a little longer. So anyway, I made a still of the horizon. Here it is. You can see that that's, you can definitely see sky between those waves. It's really funny how it's as if the horizon just stops. I mean, the ground plane angles up, and when it intersects with your eye position, it stops. I mean, you can see right between the waves. It's as if it's one layer of waves, right? Look how you can see the sun between those big gaps between the waves. If that horizon were the result of a very gradual curvature, the horizon would be much thicker and much denser. You wouldn't have that kind of definition within the waves. Okay, see the people on the boat? They're just a layer of people, one layer, and see how they look like the horizon? It's as if the horizon is very thin and it just drops off. This is kind of blurred out, but you can see the upward trajectory and then the thin horizon. There's no depth to the horizon. It's as if it stops, and it does. Perspective would dictate that the ground visually angle up to your eye position, and when it does that, it stops. You know, you can't see any more ground behind it. You can see things beyond it, but you can't see the ground. And notice how the waves can block several floors. I mean, 4, 5, 6 stories of those buildings. And the further away the buildings are, the more of them gets blocked. It's like holding your thumb out at arm's length. You can block things much bigger than your thumb. Again, here notice the thin horizon. It's very choppy. You can see through it. You can see between the waves. And notice on the right-hand side how when the water splashes up in the air, it falls back down on the water and it's obscured by the horizon. Again, that thin horizon is strong evidence that we're on a plane and this is perspective because of the fact that the horizon just drops off. It stops. It ramps up to your eye level and stops.